In Part 10, we solved recurrences by repeatedly expanding equations, but algebra often hides the true structure of an algorithm. We can map that structure directly using a visual blueprint called the Recursion tree method. To build one, we follow a four-step framework. First, draw the tree of recursive calls. Second, compute the cost per level. Third, find the total height of the tree. And finally, add all those costs together. By mapping these steps, we can calculate the exact time complexity of divide-and-conquer algorithms without getting lost in long, repetitive formulas. Look at this diagram for the binary search recurrence, T of n equals T of n over 2 plus 1. Notice how the problem size shrinks by half at each step down the tree, from n to n over 2 to n over 4. But look at the right side. The actual work done at each level remains exactly one operation. To figure out how far down this tree goes, we stop when the problem size reaches 1. Setting our division, n over 2 to the power of k, equal to 1, and taking the log base 2, gives us a tree height of exactly log n. Since we perform one unit of work across log n levels, adding them all up yields a total complexity of theta of log n. This next structure shows a different recurrence. T of n equals T of n over 2 plus n. Here, the work done decreases alongside the problem size. The cost column now reads n, then n over 2, then n over 4. Adding up these decreasing fractions creates a pattern. We calculate this sum using the infinite geometric series formula. With our ratio r set to 1/2, the calculation resolves cleanly to a total cost of 2n. Because the total sum converges to 2n, we can drop the constant multiplier. The overall time complexity simplifies directly to theta of n. Now we examine the recurrence for merge sort. T of n equals 2t of n over 2 plus n. This diagram shows how the tree branches at every level. Our starting node n splits into two n over 2 nodes, which then split into four n over 4 nodes. If we sum the costs horizontally across the first few levels, a pattern emerges. Level 1 gives us n over 2 plus n over 2, which equals n. Level 2 gives us 4 times n over 4, which also equals n. Notice the pattern. Despite the branching, the total work done at every single level is exactly n. We already know from our division by 2 that the height of this tree is log n. We multiply that constant per level cost of n by the total number of levels. Doing n work across log n levels guarantees an overall complexity of theta of n log n. This makes merge sort the quintessential divide-and-conquer algorithm. Let's test this logic on a recurrence where branching outpaces division. T of n equals 4t of n over 2 plus n. Pause the video and try to manually calculate the total cost for level 1 and level 2. Drawing out the structure, the tree cascades aggressively downward. A single node branches out to 4 nodes, which then explode into 16 nodes. The horizontal sums are now growing rapidly at each step. Level 0 is n. Level 1 calculates 4 times n over 2, giving us 2n. Level 2 gives us 16 times n over 4, reaching 4n. In recurrences where branching heavily outweighs division, the cost inflates as you go down. The bottommost level dominates the total computational cost, resulting in a complexity of theta of n squared. The Fibonacci recurrence, T of n equals T of n minus 1 plus T of n minus 2 plus 1, subtracts from the problem size at each step instead of dividing it. This shift causes an unchecked exponential explosion of recursive calls, where the number of nodes essentially doubles. Because the tree width doubles endlessly, the total work multiplies out of control. The algorithm falls into an exponential time complexity of theta of 2 to the n. The recursion tree method provides visual, mathematical proof of how algorithms consume time across different levels of execution. This chart maps out the most common divide-and-conquer recurrences to their proven complexities, giving you a reliable cheat sheet. While these visual aids are excellent for understanding, sketching elaborate trees is often impractical during a timed exam. Part 12 introduces the master theorem, a direct formulaic method used to solve these same recurrences through simple comparison.